For years, engineers have debated the best way to build large software projects. Should we optimize for developer efficiency and scale everything into a single monolith? Or should we make scaling the software easier and separate concerns into smaller microservices? Here at Meta, we've been a monolith shop since Facebook started in 2004, and it's served us very well, but generative AI has thrown some wrinkles into the mix. I'm Zach Zundel, and my colleague Phil Lopreiato and I are going to explain exactly how we made www work for the generative AI use cases. We are on the Web Foundation team, which is one of the teams here at Meta that takes care of the monolith. We tend to spend our days investigating the many weird things that happen inside production www and making sure that it runs reliably for the billions of users that use it to connect with each other every single day. So in 2004, Mark Zuckerberg started writing PHP in his dorm room. In the intervening 21 years, we've only doubled down on that approach. We wrote Hack and HHVM to make the PHP code more efficient and easier to write. Dozens of teams at the company have worked on improving the developer experience to make building new products fast, scalable by default, and efficient. Our approach here has paid off, and this is not just one website anymore. Our monolith powers every single product at Meta. Every product uses the monolith because it mediates access to the social graph, which powers the experiences our users love. We've built frameworks to hide the complexity of planet scale and make it possible to build enormous apps like Threads without getting smacked by the growth hockey stick. But all of this winning comes at a price. We're victims of our own success in some sense. www is now about 600 million lines of code. And this is 600 million lines of Hack, which is an interpreted language. That means that it is slow to run code for every single request because we have to interpret every single instruction on the fly. Of course, doing this in production would be a little bit silly, so we do JIT compile the hottest paths down to machine code, but we can't do this for everything because this machine code takes up memory on the machine. If we want more machine code, we have less memory left over on the server to actually handle requests. If we want less machine code and more memory, then these requests run slower. Both of these cases mean that we need more servers to handle our peak load, and we have to pay more money for these servers. The scale of www means there's no simple answer here. We're always trying to balance the memory that our requests use with the memory that we use for machine code and make sure that runtime is fast throughout. One of the engineers here likes to joke that HHVM is only CPU constrained, provided that you have enough memory. The other thing that's important to know about www is that it's extremely asynchronous. In one sentence, the most common request is to fetch some data from the social graph, run privacy checks on it, and return the result to a user. Of course, we do way more than one fetch for a given request. And it's really time to come clean. We're not just a monolith shop. We also have a huge service mesh behind www to power things like ads, feed ranking, messenger mailboxes, and more. A given request will dispatch hundreds to thousands of fetches and RPC calls to serve the user. We want to make sure that's very fast because nobody likes to wait for tens to hundreds of seconds for their feed to load. To make this fast, we use cooperative multitasking. Let's see what this looks like for a normal feed request. So you'll send us a feed request with an auth token saying that you are who you say you are. The first thing that we'll do is we'll send an RPC to the login service to make sure that this auth token is actually correct and that it identifies you as you. While we're waiting for this response to come back, we'll preemptively send a request to our social graph cache for your user profile. We'll need this user profile to begin hydrating your feed. While we wait for both of these requests to be processed, there's not much we can do, so the worker thread will sleep. Once the login request comes back, validating that you are in fact who you say you are, we'll begin hydrating a login credential for your user, which we'll then use to run privacy checks for the rest of the request. And here comes your user profile. With your user profile, we will be able to run the privacy checks using your login credential and start hydrating your feed. We're off to the races. HHVM runs these tasks concurrently, but not in parallel. What does this mean? This means we have exactly one thread handling your request, and that thread is only going to work on your request until the end. This thread will either be handling CPU work to schedule or process the results of I/O operations, or it will be sleeping. And while it's sleeping, we do not let it handle any other requests so that it's available to process the results of your in-flight I/O operations when they return. Because we have not yet invented a CPU with infinity cores on it, we have a finite number of these worker threads on any given machine. Even if we had such a magical CPU, we also have finite memory on the machine, so we can only have a fixed number of requests in flight at a time without running out of memory. Finite worker threads, plus tight coupling of these threads to requests, means that we essentially have a finite number of slots on any given server to handle requests. We need to limit how much time any given request can sit in one of these slots so that we do not overload the fleet with long, slow-running requests. We give each request 30 seconds of runtime and then we kill it. The other thing that we're trying to do is make sure that every server has as many slots as possible. We are naturally bounded here by the number of CPU cores and, most importantly, the amount of memory in each given server. We don't want to overcommit memory too much, so we make sure that we limit the amount of memory every request can take to 334 megabytes. This means that we can roughly calculate the number of request slots a given server can handle by looking at how many cores it has and the total amount of memory on the machine. These two rules, 30-second runtime and 334 megabytes of memory, are as close as we get to laws of physics in dub. Our team has found that even small exceptions to them dramatically impact our reliability, so we hold this line as aggressively as we can. We do not let people run requests for longer than 30 seconds, and we do not let them use more than 334 megabytes of memory. How do we reach these numbers? The answer is, we used to not have limits. These cause reliability problems. We started with high limits, and we've cranked them down over time. These limits do not just make it easier to run the site reliably, they also improve the user experience. It would not be a great experience for you to have to wait for a minute or 2 minutes for your newsfeed to load, even if the result of the newsfeed was much more engaging to you. So the 30-second runtime imposes some sort of overall latency constraint on making sure our site is very responsive. Like everyone else, however, our world is flipped upside down with the advent of generative AI. Phil is going to talk next about what's really, really different about the generative AI workload that makes these laws of physics a little bit looser. I'll then tell you about how these differences actually physically manifested in some of the products that we wanted to launch. And then Phil will close out by explaining how we solved all of our problems by tuning HHVM and also reconsidering these laws of physics inside dub.
Thanks, Zach. The first thing to note is that the workload for GenAI traffic is fundamentally different. GenAI requests run a lot more I/O than normal ones. Here, we can see the breakdown of the amount of time that GenAI requests spend blocked on I/O, about 90% of their time, compared to what normal requests do, more like 70. HHVM has only one worker thread per request, and each of these threads are doing less work here because they spend a greater proportion of their time waiting on data to come to them and wake them up. This means that the overall web server has higher thread utilization because threads don't complete their work as quickly and get released back to the thread pool as quickly as they would otherwise. This makes it more difficult to saturate the server because those threads are not being used as much. The limiting factors of GenAI traffic are first thread utilization, then memory, then CPU usage for GenAI work. The user-facing expectations of the product are also different here. When you're interacting with an LLM, you want that process to feel interactive and engaging. Having a lot of dead air waiting on results to come back to you is a bad thing and a bad experience, and we don't want that. We care a lot about the time to first token of the response, where the model sends its first initial bits of data back to you so that the conversation can seem engaging. But also at the same time, the total runtime request can be longer, while we wait for the completion of the response to stream back to you all the way. Here, we can see a CDF of the latency distribution of GenAI requests versus regular ones. The thing to note is that the GenAI traffic has a much longer long tail in how long they can take to execute. This is a different aspect of the workload that we'll have to support in our infrastructure deployment. One way we can do that is to use the async tier. And this is another advantage of running in the monolith. It's easy for us to compose building blocks of systems that already exist, so we can iterate quickly and get a sense for what things work and what things don't. Here's a system diagram of the async tier, which is designed for long-running but not user-facing requests. This means they have a longer request timeout so they can do things like background processing. Initial prototypes of the product use the async tier to work around runtime limitations and avoid requests timeout that would come along with running on the front end normally. However, the async tier also incurs some queuing and dispatch delay before requests start to execute. Technically, this is not a problem for offline work, but affects time to first token in the responses that come back from the LLM. It was okay to use the async tier for initial prototypes, so we could build up everything around the AI products, but we also wanted to make sure that we were able to build out the fundamentally optimized infrastructure in parallel that we can migrate on everything else onto later. After this, Zach will talk about how products benefited from those later improvements we built.
Thanks, Phil. Now that we have a way to build GenAI products in dub, we can unleash the collective might of our product development teams. Nobody has to learn a new tech stack, and it works great, until it doesn't. One of the first use cases we had issues with was smart glasses. These are our meta stories with an inbuilt AI assistant. We wanted the conversations with the assistant to feel natural, and it's not very natural to wait 15 seconds for your conversation partner to reply. It was important that the first words the model generated were streamed to you very quickly, and then each subsequent word was streamed to you as it was generated. It was no longer reasonable to wait for the full AI response to be generated before we returned it to you. We needed streaming. The other issue we run into is that we got better and better at building models, and these models got larger and larger. As we released models with billions of parameters, these models ran more slowly and regularly exceeded the 30-second law of physics runtime in dub. So let's talk about streaming. The async architecture Phil described had a queuing delay at the beginning. This queuing delay does not exist in production dub, but production dub only understands HTTP request and response. We do have a way to stream data in and out of prod dub with GraphQL, but we're not using GraphQL here. We're making thrift RPC calls into dub, and the thrift HTTP transport does not understand streaming. So what do? Do we teach thrift over HTTP how to understand streaming? Or do we teach HHVM how to use a different thrift transport like Rocket, which does support streaming? Since we work here at Meta, our first answer was to do neither of these and do something a little bit hacky. We built a middleman service which speaks Rocket over thrift to the clients, so the clients have a streaming API that they're familiar with. This service translates the Rocket thrift request into GraphQL requests that it makes to dub, so that dub can stream the data back into the service. This works, but it's pure overhead, so we need to do something better to make sure the latency of talking to your smart glasses is low. So, what do? We clean up some tech debt. We, on Web Foundation, have wanted to get rid of thrift over HTTP for a while. It's a poorly supported transport internally, and it doesn't get a lot of the nice new features that the thrift team is building. Now it's important for the business, so we're going to do it. But where do we start? The first thing that we did is create a new, smaller deployment of the monolith just for GenAI. We did this so that we could experiment with the transport without affecting the rest of production. This also had some side benefits from the beginning. The first side benefit is that we had to decide where to physically place this smaller deployment. We decided to co-locate it in data centers where we had GPUs running inference. This meant that we cut down on network hops and we optimized around the expensive GPUs rather than the cheap web servers. This made our models faster, and Phil is going to describe the rest of the tricks that we use to make GenAI run better in the monolith.
By default, inference can take longer than 30 seconds. This means we need infrastructure that can support that. We want to optimize for that highlighted part of the latency CDF, where the requests are taking a little bit longer than typical, but are still executing more than the immediate result. The async tier has too much initial delay before it starts to actually process the request, so that is also unworkable from the perspective that it takes too long to get the first data back. The solution here is to run our own web tenant that has a longer request timeout. This is not particularly novel, but that does let us support workloads that have fast initial latency and also a longer runtime. We were able to slowly bring products one by one onto this dedicated tier with a longer timeout as their models got complex enough to require the additional runtime. This didn't really come up to be mission critical until Connect 24 last year when we launched the 4 or 5 billion parameter model, but we knew this was coming. As model development got more and more complex over time, we could see the runtime approaching the limits that we knew it would hit eventually. This allowed us to take time to invest in the correct infrastructure early, so we were able to seamlessly support this once the lines crossed. Next, we also have to tune the size of the thread pool. Doing more work on I/O means that we need a larger thread pool on the web server in order to support that, while also keeping the CPU as busy as we can make it. Because once again, requests are tied one-to-one to HHVM worker threads. So, when the requests are suspended waiting for I/O to return, they are not busy. The solution here is similarly trivial. Add more threads. We can compute the number of this based on how much memory is available on the server, and divide the total amount by the per request memory limit, and we end up with about 10x more threads than a normal web server does. That's okay, because these threads are all suspended, not doing much actual work, and it keeps the CPU utilization much more consistent and allows us to use our available capacity where we can. HHVM is also an interpreted language. This means it keeps a just-in-time cache of compiled machine code of all of the instructions that it executes. This compilation happens the first time it gets executed, and then stored in memory so we can execute faster the second time. The corollary here is that running the same code over and over again is faster than running many types of requests only once at a time, because it lets us amortize the cost of compilation over many, many requests. We have a solution called Jumpstart, which allows us to borrow the JIT cache regions from other already warmed hosts. One of the other benefits of running in the monolith is that we can take Jumpstart profiles from production web servers and apply them to the dedicated GenAI hosts, which allows us to use the pre-compiled instructions from costs amortized from somewhere else. And this lets us ensure that the core frameworks both tiers rely on are warm. This is one of those key benefits of the monolith that lets us move faster here and more efficiently. We can additionally, on top of this, run more static requests at server startup in order to warm cache with the code that is unique to the dedicated tenant. We can run dedicated requests as part of server startup, but before it receives user traffic. We wrote a handler to execute all the code and send some dummy traffic to the models and throw away the results. This is okay from a capacity perspective because the tier is still pretty small, so the overhead is not that big. But using real requests here allows us to warm up all of the other runtime resources that might come into play. Think other thread pools or other caches that might be different from JIT. And again, now that we are ready to then serve user requests next, those resources are all ready for us, and then we can execute without any further startup costs when that latency is visible to users. Finally, we can also run shadow traffic. While the tier is still small, this allowed us to increase the traffic baseline, again, for better JIT coverage. Because sometimes code gating is dynamic in the application, the static warm-up requests we ran when the server started might not still apply sometime later. Some products have their own inference orchestration service that makes requests to www. Here, we were able to send multiple requests, even again if some responses are discarded, but those multiple requests allow us to execute that code on multiple servers, therefore ensuring that they stay warm for the real requests that come later. Again, the capacity overhead here was not substantial because the tier was still small. But as organic traffic increased enough in order to keep the tier warm in the steady state, we were able to turn this down later once it was self-sustaining. As a result of all of this work, we were able to learn that by focusing on full stack optimization of the system that we deploy, we can deliver something that is effective and optimized up and down the stack for every step along the way. We can maintain the developer experience of working in a monolith, which allows developers to operate as efficiently as they can by relying on the same environment that they use every other day and not need to learn anything special or make any special assumptions about working in this specialized environment. We can also keep the operability of microservices, where we can deploy different tiers with different configurations to meet the needs of all of the workloads and the traffic that they serve. We do this by effectively tuning HHVM to meet all the requirements of the system again, where we can have a longer runtime limit, we can have an increased size of a thread pool, or we can have better tuned JIT cache to make sure that we can deliver the best performance possible for all of the machines that we have, which allows us to deliver a well-functioning product at scale. And finally, we can deliver a better product experience. These optimizations make the product 30% faster, while also letting the product teams play to their innate strengths to iterate quickly, find a product that works, and get it out to users as fast as possible, all while assuming that the infrastructure underneath them does the right thing and that the system will perform efficiently underneath it. Finally, we've also completely removed timeout limitations as being something that we need to worry about when shipping larger and more complex models, which is something worth celebrating all of itself. If you'd like to learn more about this, feel free to check out the blog online, and thank you for your time.